And according to this, if they both have the same average speed, then for each car's path, there's somewhere where this will be tangent, right? But see, the two cars have different paths. So my question is, okay, do they ever travel the same speed? Yes, right? There is a point where they both will travel the average speed. But is it the same point in time for both cars? So think about it, and then we'll take a vote. Does anyone have a question about the question?
I thought you were first
Yes.
asking their average speed.
Pardon me?
They have to be at their average speed at the same time.
Well, I'm not saying that it necessarily has to be their average speed. Let me draw this.
Yeah.
Let's say we have this blue car, right? We have this blue car here. I've already used red, okay? So the car starts the race and ends the race, right? And so that red would be its average speed. And everyone kind of agreed that there would be, in this picture, a few places where this tangent line would be parallel to the red line, right? I'm going to draw you now a different car, okay? A different car's path. Here we go. All right, do they both start at the same time? Yes. Do they both end at the same time? Yes? Is there a place on this curve that we are tangent to the red line? Yeah? You'll see it. It's somewhere around, maybe here? I don't know. I'm just kind of guessing. Somewhere around here? So if you look at the cars separately, this car here, there's some point in time where we will be parallel to the red. And on this car, there's some point in time that this will be parallel to the red. My question is, will it be the same point in time for both cars? No? Does anyone needs clarification on the question?
Well, I thought you were asking it first. Was there any point in the race where they'll be going the same speed at the same time?
That's exactly what I'm asking.
Yeah.
Okay, other than the start of the race and the end of the race. Because look, at the beginning, they're both sitting there going 0, right?
Yeah.
Okay, so not there. And at the end, also, I want you to not consider the end of the race either when they cross the finish line. Because when they cross the finish line, they're tied, right? So you could argue maybe that they're going the same speed. I'm saying sometime in between, in somewhere within the race. After it starts and before it ends, can you guarantee me that there's some point in time, the same time for both cars, that they will be going the same speed? Any other further questions?
I'm just like, I'm thinking kind of yes, because I mean, essentially it's just two cars and one car is accelerating one.
Mm-hmm.
One is going at a constant. One looks like it's going at a constant speed, and the other one looks like it's like speeding up.
Don't worry about this picture. This picture was just to get the idea that they start together, end together. This could be, I did this in like 5 minutes through this together. So I could spend more time and make one car, make them kind of go like, and I could do that. I just didn't have time to put that together, okay? So, y'all ready? Oh, questions?
So the question is if they go the same speed at the same time?
Is there a point in time, for both cars, the same point in time that they must be traveling the same speed? Is that guaranteed to happen for this type, in this particular race? Huh? Well, the same point in time, not that they're not necessarily at the same place, but it's the same point in time. So it's the same point in time. So you think so?
Yeah. As long as it doesn't also have to be the average speed. If it's a random speed and they're going, If they hit a random speed at the same time, yes. Yes, they go.
Okay. So let's take a vote. I mean, this is not part of your grade, okay? There's a point to this. How many of you think that, yes, there is some point in time for both cars that they will be traveling the same speed? How many of you think, no, it's not possible? You agree with that? Okay. Okay. Normally what happens in a class is that I get about half the students that are like, yeah, and then the other half like, no. And there's this big conflict, and there's a debate. There's no debate here. So I guess we just agree that that's the way it is? If enough of us agree, then we agree. Right? So I think this is a problem that is counterintuitive. I mean, all of you agreed, but I think it is counterintuitive. I think someone can make a pretty good argument that it's not going to happen. Let me draw you a different picture. I'm going to try and challenge all of you because apparently all of you think this is going to happen.
Yeah, it's like a proof that sort of like there is a specific.
Okay, so here we go. We have a race, right? Let's do the blue car. The blue car is going to start here and end here. And I'm going to have its path look like this. Okay? And then I have my red car. My red car is going to go like this. All right. From that picture, show me the point in time, somewhere here on the axis of time. Show me where the two lines are parallel. Because basically what you need is for them to both have, somewhere for them to both have the same tangent line, right? Because the tangent line is going to be their speed. So in the beginning, right, look at the tangent lines. Are they ever parallel?
Yeah.
Where?
Yeah, exactly.
Where?
The curve.
Yeah.
The where?
The end of the curve.
The end of the curve? Like,
Yeah.
all right, there. Where? Do you see what I'm saying?
What is that?
Like, I can sit here and try and draw it. As soon as you like say it's right there, I can probably change my graph a little bit and it's not there anymore. You know what I mean?
I feel like the argument goes the other way too. Like if we're starting at the same time and ending at the same time, there is, even if it's super small, there's a time where, especially if the red car started going super slow, there's a time where we end, and let's say the blue one goes pretty average. If we're ending at the same exact time, there is a time where we are at the same speed, even if it's for a small amount of time.
Let me do this. I'm going to exaggerate the shit out of this, okay? There, like that. And then I'm going to make this one go like this. Okay? There. Show me the point in time where they're parallel. Look. So it has to be the same point in time. So look, let's pick right here. Right here? In the middle?
More or less, yeah. Yeah, pretty close.
Right there?
Yeah.
Yeah? Somewhere around there? So what if I change this to this? Ooh, that's a good one. Where's that happening?
Over there.
Where? Somewhere over here? They'll have the same?
Yeah.
Yeah? Yes?
So like, I guess the thought process of why it must have, they must be the same speed at least at some point is because like, if one, let's say like car is like slower than the other, it lags, or I guess we can look at the movement picture. So one is like starts off super slow and it starts to accelerate while the other one's at a constant rate. But eventually it will have to speed up to catch up because they both end at the same time.
Yes.
So eventually they'll have to cross paths, so to speak.
Lights. Yeah, so we could sit here and verbally try and convince ourselves of this, right? And then have someone try and challenge you, and then, right? And we could go back and forth. And this is exactly where mathematics is important in the real world. Because we don't want to build a tree, build a bridge or an airplane on a hunch. Yeah, I think that bolt will hold the wing on. It seems strong enough, right? That's not the way we do things, right? There has to be mathematics behind it. So this is a great example of, I'm going to be able to prove this to you, all right? What the correct answer is. But I have to be able to prove it to you. That way anyone who doubts it, I have a proof, all right? So to prove it, I actually need to first show you the theorem for this section, which is what this section is called, the mean value theorem, all right? Eventually, I will convince you what the answer is. I'm not going to tell you what it is yet, but I will convince you, hopefully. So we've got some pictures to look at here. We actually have two theorems in this section. We have what's called the mean value theorem. We have what's called Rolle's theorem, and then we have the mean value theorem. So we're going to start here with Rolle's theorem. Rolle's theorem says this. And a theorem, remember, a theorem in mathematics is a statement that has been proven to be true using our logic system, our number system. There's a rigorous proof that shows that this is always true. Now, I think once you see it, you'll agree. It's not a stretch. So first we have to have conditions for this theorem. Let f be a function, okay? Let f be a function such that f is continuous on a closed interval. Right? So that means we have a function that I'm going to be able to draw it from A to B, right, on a closed interval. I'm going to be able to draw this without picking up my pencil. All right? That's the first condition. We have to have a continuous function. Second condition is that the function is differentiable on the interior. That means I can take the derivative everywhere inside. That means when I draw the function, not only is it continuous, I don't have any corners, cusps, anything that would screw up the derivative, right? I don't have any of that happening. The derivative exists everywhere in here. Got it? And then the third condition, and the most important one, is that f of a equals f of b. That just means that whatever my function's value is at a, that's f of a, it's the height of the point, right? It's also equal to what happens at f of b. I mean, that's also what happens at b. So these two values are the same. So I'm going to draw this from here to here without picking up my pencil, and I can't have any corners or cusps or any weird shit happening that screws up my derivative, right? So I draw it however I want. So I'm going to draw a very simple one from here to there, like that, right? Rolle's theorem says if these three conditions are met, then there must exist some number c in between a and b such that the derivative is equal to 0. So do you all agree that there's a point? The derivative being 0 means that my tangent line is what? If I said the derivative of a function is 0, that's the slope of the tangent line, right? Which means that the slope is horizontal. Do you all agree that there's somewhere in here between here and here on this curve that when I look at the slope of the tangent line, it's going to be 0? Somewhere, right? It looks like it's about right here. See? Slope of tangent line, 0, right? Let me draw a different curve for you. I'm going to have it start at A, end at B, have start and end at the same point, and now I'm going to draw it connect together, right? However I want. Just no corners or cusps. So how about this? How about I go like that? If I do that, do you all agree that there's at least one point? This says there exists a number, right? Some number inside that the derivative will be 0. Do y'all see a point? Maybe about right there. C, right there. Derivative is 0, right? Is that the only point? No, there's a couple in this one, right? Here, 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 right? The theorem, the theorem guarantees the existence of at least one point. There's at least one. You might have 3. You might have 20. The theorem says there exists at least one. So I have pretty much what I just drew there. There's an example, right? So what we're saying is that if you connect the two, if these two, the key is that the two endpoints have to be the same height. These two endpoints have to have the same height. Because what we're essentially doing is we're saying that if you connect these two endpoints together with a straight line, we're going to find a tangent line parallel to that line. If we connect these two with a straight line, we're going to find lines that are parallel to that line. Does that make sense intuitively? So it doesn't matter how we draw it. Well, it does. We can't have any corners or cusps. This is a second example, right? Our tangent lines there are parallel to the line connecting the two endpoints. Third example, hey, a straight line. A straight line connecting these two. Every point in here qualifies as a C, because at any point you pick in here, it's parallel to the straight line connecting the two endpoints. That's Rolle's theorem. Yes?
Can you show the theorem again?
Can I show what?
The theorem?
Okay, that's Rolle's theorem. Got it? Now, what's that?
We did not have to do with the cars.
It's,
The points were different.
the points were different. That's correct. All right, now, well, yeah, yes and no. You'll see how I prove it. I'm going to wind up using Rolle's theorem to prove it. But so does anyone disagree with this concept? Does it seem reasonable that we can accept that theorem? All right, that leads us to the next theorem, which is called the mean value theorem. Now, when you see the word mean, okay, we're not talking about like mean like a person who's unpleasant, right? We're talking about average. Mean is another word for average. So when you talk about the mean value theorem, we're saying really the average value theorem. And I started this whole discussion saying, hey, if we drive to Austin, right, 80 miles in 2 hours, our average speed is 40 miles per hour. Is there a point in time where we had to have gone our average speed? Yes. This is the theorem that guarantees that. All right, so let's look at the conditions. These are different conditions. Different theorem, mean value theorem, not Rolle's theorem. Let f be a function that's continuous on a closed interval ab. So we again have the idea of continuity, right? So we're going to have a function that when we draw it, we're going to be able to start here at a and end here at b. Now, we need differentiability, again, also on the interior of the interval. So we need to be able to take the derivative on the inside. That still is a condition. So no corners, cusps, or weird jaggedy edges. But look at the result. Notice this does not have that condition that the two endpoints have to be at the same height. That condition's not here. But look what it says. Then there exists a number c in the interval such that, look at the left side of this. That's the slope of the tangent line, right? That's saying the slope of the tangent line, somewhere in there, the slope of the tangent line has to be equal to that. Do you recognize that? So I have 2 points, right? I have no conditions on these 2 points. This is the point A, f of A. This is the point B, f of B, right? Plug in B, right? B, plug it in, get f of B. A, plug it in, get f of A. What is f of B minus f of A over B minus A? Not,
Like that's what we were.
no, that's a limit. That's if we took a limit. This is before the limit. If I tell you to take f of B, subtract f of A, and then divide that by B minus A,
You lost it?
no, what's the slope of that line? Rise over run? What's rise? Difference of the y coordinates, right? If I wanted to find the slope of this line, you do rise over run. The rise, I really don't want to put this on here, but I will. This right here is your rise, right? That's the difference of your y coordinates, isn't it? That's f of b minus f of a. Your run is your difference of your x coordinates, right? B minus a. So isn't the right-hand side of this equation the slope of the line connecting the two endpoints, right? This right here, this right side, is the slope of this green line. Y'all following this or not? We have a curve in here. I haven't drawn the curve, have I? I have not drawn the curve. We have some curve in here I'm going to draw. And the theorem says that no matter how I do this, as long as I connect these 2 points together, somewhere in here, the slope of the tangent line at that point will be equal to the slope of the line connecting the two endpoints. So I will have the picture I drew for you earlier on the trip to Austin, right? I will have this happening at some point C. They'll be parallel, right? Now, I'm going to show you something. I'm asking you to believe that. Nobody had an argument with Rolle's theorem, right? Everybody was happy with this idea, like it made sense to you? Because the 2 points were at the same height it makes sense that I'm going to have a little hump here and that I'm going to have a flat tangent line, right? No one had a problem? All the mean value theorem is Rolle's theorem, okay? That's Rolle's theorem. It's Rolle's theorem, but we're allowed to just kind of like turn our heads, right? Y'all see that? It's just Rolle's theorem twisted. That's Rolle's theorem. Two endpoints have to be the same. If I change the right endpoint, then notice how that has to be, it's no longer 0, right? But it's definitely, it's the derivative at this point, and it's parallel to this line. That's the mean value theorem. Got it? Make sense? If I change this, oh, that doesn't work. That one doesn't work. That's not a function, fails the vertical line test. Okay? So let's do an example, all right? Let's just do an example so you can kind of see where we're headed with this, or the type of problem you would see maybe on an exam. Example, verify the mean value theorem, MVT is the abbreviation, for the function f of x equals x squared plus 2x minus 5 on the interval, let's just go -1, 3. I'm going to put the mean value theorem back up here. Suppose we have a function that's continuous on a closed interval. Then there exists some number c such that the derivative is equal to this, right? So let's start with the conditions. We're asked to verify that the mean value theorem is true for this. So is this a continuous function? Why? It's quadratic. All polynomial functions are continuous on all real numbers. So this is a continuous function everywhere. So if we restrict it here, it's definitely continuous. So I have the first condition met for the mean value theorem, right? This is continuous. This is continuous. F is continuous on the interval -1, 3. Check. All right. All right, second condition. The derivative, the function is differentiable. Well, let's look at the derivative. What's the derivative? The derivative of that is 2x plus 2. Is that a nice function? Does it have any problems? There's nothing like, oh, we can't plug 2 into that, right? Like, it's a nice, well-defined function. So the derivative exists everywhere in that interval as well, right? So I have the conditions that I need. The mean value theorem should apply to this function on that interval. I want to show you graphically what we're doing right now before we actually do this. We're taking the function x squared plus 2x minus 5 on the interval -1 to 3. We're looking at that function right there, all right? Let me put the points in there. -1, what does that look like? -6. And then the other point is 3, 9, what is that, 10? Okay. All right, so we're looking at this function, right? Between -1 and 3, right? And we're imagining that if you connected a straight line between those 2 points, right? Connect straight line. There's somewhere on this curve where my tangent line will be parallel to that, right? The average value of this function is the slope of the line connecting those 2 points. That's the average value of the function. The mean value theorem says somewhere in there, in the interval -1 to 3, I should find a point where my slope of my tangent line will be equal to that average value. So how do we do it? Well, the mean value theorem, right? Mean value theorem says there exists a C in the interval -1, 3 such that f prime of C equals f of B minus f of A over B minus A, right? That's what the mean value theorem says. I've taken it down, but yes, that's what it says. Do we know what A and B are in this problem? Yeah, do you know what A and B are? Yeah, they're given to you, right? This is A, and this is B, right? So let's start figuring out, we're going to treat this like an equation, and we're going to work the left and right hand sides together. What would be the derivative of this function at C? So here's your derivative, right? Plug C into that, and what would you get? 2C plus 2, right? So this left side becomes 2C plus 2. That must equal, according to mean value theorem, that must equal what? F of B. F of B is 3. F of 3 minus f of A is -1, f of -1 over B, which is 3, minus A, which is -1. This is a number, right? This is a number. That's a number. That's a number. This whole right side is a number, right? I have 2C plus 2 equals a number. I should be able to solve that for C, shouldn't I? I'm going to keep working over here. So I have 2C plus 2 must equal, what happens when you plug 3 into the function? You get 10, right? I erased it, but it's up there, right? We had it on the graph. When you plugged in 3, you got 10. So this top left is 10, minus what happens when you plugged in -1? Do you remember what I got? I think it was -6, right? Yeah. And then over, the bottom is 3 minus -1, that's just 4. Isn't that 16 over 4? 16 over 4 is 4. So 2C plus 2 equals 4. Solve for C. Subtract 2 on both sides. C is 1. I made this problem up. I'm surprised the number came out to be nice there. So C is 1. C is 1. Now, I'm going to show you. Oh, is 1 in the interval? I should point that out. Is 1 in here? Yeah, right? So let me do this real quick. It's going to take me just a second. First thing I'm going to do is I'm going to draw the tangent line. Nope. What the hell? What was the right side? 4? There we go. All right, that's our tangent line. I'm sorry, I said tangent line. That's our secant line, right? Connecting those 2 points. Right? That's the line connecting the 2 endpoints. I'm trying to figure out where on this curve I'm going to have a tangent line that's parallel to that. And we just said C is 1. So let me do something here. Whoa. So now what I've done is I've made a little slider here that I can animate this, and I can move my tangent line around. Okay, see that tangent line there? I can move that along the curve. And I'm going to go to 1. I'm going to go to where the x coordinate is 1, which is right there. right? This is 1. If I go to the point on the graph and I draw my tangent line, they're parallel. Got it? You have a question on that? Verifying the mean value theorem is strange because it's like, you are solving something, but it's the way you set it up. You take the derivative of the function, you plug c into it, and then you just compute this. This is a number. And then you solve this equation. Yes?
On the test, did you give us a graph so we can determine the endpoints?
No. You would have to determine them. But I mean, all you have to do is plug 3 into the original function, right? 3, like the original function was x squared plus 2x minus 5 or whatever. So just plug 3 into it. I'm going to do another example. This one was pretty straightforward because it was a quadratic function. So things were nice and the equation was pretty simple to solve, right? That was a pretty easy equation. Let's do one more of these. Hey, by the way, there's going to be 2 homework problems with Rolle's theorem. And the only difference with Rolle's theorem is that with Rolle's theorem, all you're doing is trying to figure out where the derivative is not equal to that secant line, but just equal to 0. So when you do the Rolle's theorem, all you're doing is taking the derivative and setting it equal to 0. That's all you're doing. This, the other one here with mean value theorem is a little different. Let's try this one. Let's graph it first. Let's look at a function. Let's do the square root of 1 minus x squared. And let's look at that on the interval -1 to 1. That's kind of boring. No. There we go. That looks fun. All right, so we have the function is 2 over the square root of x. And we're doing it on the interval, can you tell? 1, 5. So f of x is 2 over square root of x. And we're doing it on the interval 1 to 5.